So, greeting for everyone. I'm starting this lecture on game theory and application. And okay, actually this lecture was like introductory, and but I get many different interesting problems, and I think that the best way to learn game theory is from your experience, first-hand experience and interesting problems. So I actually plan some games we can play and then see the results, and I will try to explain it. And before we start, I will give you some plan about this today 2 lectures, but I consider this like 1 lecture. This interruption. Okay, so first we start with the history. What is game theory? How it were created? Who was responsible? Then about main fields, main direction of applications. Then we play some games, and I will try to explain your notation and how, well, the main ideas and the main concepts that game theory is about. And actually some different types of games, actually many types of games. Then we will go to the game in extensive form. And at the end, I will tell you a little bit about behavioral game theory, which is like sideline, but it's really interesting and it's good for the end of the lecture. Okay, so the idea of this short course is to give you idea how the game theory is working and what is the goal of game theory, what is the possibility, capabilities, what game theory can and what it cannot, and how you can use it in your research. So game theory is about strategic decision making, and this brings it to the some unique position where you can apply game theory in every field where you have decision making of some agents. It can be humans, persons, organizations, programs, I don't know, algorithms, and anything you can imagine. So the game theory is like on the border of mathematics, because it uses rigorous mathematical methods, and economy, because economy is like biggest probably field where decision making is happening, and it's important for us. And also recently algorithmic game theory is about how to calculate. So game theory is a theory basically, and the aim of this theory is to find conditions of equilibrium, predict outcome, and calculate solutions for rational players. So we have some special assumptions, and game theory is quite harsh, criticized for these assumptions, but game theory can actually predict outcome in many situations, even if people not really rational as it seems. And the second line, which recently started to be very popular, is when we have equilibrium, is how we can calculate it. So what is the algorithm to calculate this equilibrium, and can we develop learning algorithm to go to this equilibrium step by step? So can we launch the procedure that players can learn during the game and slowly go to the equilibrium or faster? So how to came to the equilibrium if we know that one exists? So applying, and I think for me, the most interesting topic is when you apply game theory to the real problem, it sometimes work and sometimes not. So sometimes real agents behave as predicted, and sometimes they do not. And actually, as there is a very interesting paper of Robert Aumann, one of the prominent game theorists, what game theory trying to accomplish. It was published in the 70s, I think. And he says that game theory is working due to some laws, but it's not like physical laws. If game theory fail in some real situations, they just say, well, it's not applicable here, it's okay. And it's really not the same as, I mean, some law of nature fails, then disaster, but game theory is okay. So it's interesting when you apply game theory to the real problem and why it fails. So why people do not behave as predicted, and what's the reason? So we start from the history, and actually the name of game theory or theory of games was due to this prominent scientist, John von Neumann. And he he wrote a book, Theory of Games and Economic Behavior, and it was like launching of field of investigation. It was in, I believe, early 50s with Oscar Morgenstern. And the idea of von Neumann was game theory investigates strategic interaction of rational agents. And every word has a special meaning here. So what does it mean? Well, agent, it's something that makes decisions. Rational agent means that this agent has some preferences on the set of outcomes for special utility function, for example, and it can understand that some outcomes are better than others. So, and this agent try to influence the situation this way that to get better outcome. So, strategic interaction means that actions of one agent influence outcomes for other agents. So this is a interaction of some sort where you can solve your optimization problem alone. You can just optimize your function, but you dependent of what other agents do. So this makes game theory so difficult sometimes and interesting, because you need you think about maximizing your own utility, but at the same time you must think about how other will maximize their utility. And if you do not do this, then some strange and sometimes funny things will happen. I will tell about that later a little bit. So just to finish with von Neumann, he was a very prominent guy, and as you know, he was also one of the father of computers, and almost many of modern computers have von Neumann architecture. So it was the same time that he invented game theory, and also he was I think father of nuclear bomb in America. And before that, he actually solved a very difficult problem in almost every field of mathematics. So he was a genius from the childhood. Then he didn't get Nobel Prize because he died from cancer in a relatively young age. And the first Nobel Prize for game theory was awarded in 1994 in economy. And this is the first three scientists who get it: John Nash, Reinhard Zelten, and John Harsanyi here. So they got it for equilibrium concept and application to many fields. So to get you some understanding about first game theory results, it was even before for Neyman. I propose you to imagine game of chess. Everyone knows game of chess, and it was actually for that time it was a very unexpected result, I think. So chess is a game. We have two players. We have sequential moves. So each player moves after he observes the move of another player. No randomness. So all moves are like intentional. So you don't have random moves. At least you don't want it. Actions here, it's moves of chess figures, and you have full information about the state of the game. So full information here, this means that you can actually start playing any position, and the history doesn't matter at all. You can play from any position to the end. But if you play from the beginning, then you know all history of moves of opponent, and you know all possible moves on this step. So you can imagine a tree. I can actually put some, if you never saw this tree before, I make some. So you have first position, and then you have 20 possible moves by white. Okay. Then you have moves by black, and you have 20 possible moves for each of white moves. So this would be quite a big tree. And this second move, third move, this complexity starts to explode. And as you know, the number of positions in chess is bigger than atoms and universe or something. So it's quite a big number. But this tree is finite. And this is the important thing. You have special rules about drawing. So you can it's actually a tree. So without any cycle. If you have the same position, you have different ways to go to this position. So you can say that it's not the same position. So sorry. So we can start this procedure from the end. We can label all leaves of this tree with black if black wins, with white if white wins, and gray if there is a draw. And the point is that you can start from the end and try to reduce this tree step by step. I mean, it's not possible right now for the complex reasons, but we can do this in theory. And we can finish at the first position and say that in chess, only 3 possible situations can be. It's white has strategy for win, black has strategy for draw, and or they have strategy, or black has strategy to win. So there's 3 possible situations, and no other situation are possible. Well, and for 1910, it was like an interesting result, and interesting that we right now we still can't calculate it precisely. Actually, this idea of the term of strategy in game theory is a little bit different than term strategy in chess, because if you play chess, you can think strategy is some idea of opening or anything, but in game theory, strategy is a full plan of movement for any possible situation in game you can meet. So to write down strategy in chess, you need first write down all possible nodes of this tree, but right now it's not possible. So more than 100 years ago, after this result, we still can't write down a strategy. Okay. So to put it in some line of game theory problems in history, I mean, I think that we can make this line. We have first problems that that game theory was concerned is equilibrium existence. What is equilibrium? I will explain later, but for now it's a good point in the game. And if you play in the game long enough, then and you want to win, then rational players usually will be in this point of equilibrium. For example, in chess, equilibrium can be draw, and when computer plays, that number of draws is growing as computers start to get better. The computer gets better, and number of draw, percentage of draw is increasing. So it is possible that in chess, draw is in equilibrium. So equilibrium is a natural outcome when rational agents are playing. Then when researchers start to understand what is equilibrium and found it in different applications and different areas, then they start to realize that sometimes equilibriums are different. So sometimes there are many equilibriums and they are not the same. So some equilibriums are efficient, some inefficient, some stable, some unstable. There are, I think, more than 20 different notions of equilibrium. So they start to idea of refinement of equilibrium. So refinement is the understanding that some equilibriums are better than other, or more credible, or more stable, or different in some other way. So, and third idea or stage was, it has names, different names. I think we can say it mechanism design, but essentially it's architecting an equilibrium. It's opposite of backward problem in some sense. When you don't have situation where you want to understand the equilibrium, but you have an equilibrium and you want that rational players who will play this game, they will be in this equilibrium. So, for example, you want that players will behave in exact way that you want, and you try to create the rules of the game where this would be their best play. And this is the mechanism design. There are many applications. I think the most famous is auctions. When you have auction, it's also a game. You have rules of auction, you have players, and they make their bidding. And there are very interesting results about the revenues of auctions and also behavior. For example, if you heard something about Google sponsored search auctions, you know that when you search something in the internet and you put in search line, buy something, then behind the scenes, they put an auction for you to get a word to show their advertising to you, and they pay second price. So the winner pays the price of second winner, and the second place pays price for the third winner, and so on. So why the second price? Well, because this auction have very, very good properties, and it was theoretically proved by Vickrey. I think that he got Nobel Prize for that. And also Myerson and optimal mechanism and revelation theorem is actually working here. Also, another interesting application of equilibrium architecting or mechanism design is a matching algorithms, where you have some sort of matching and you want that people who use this matching algorithm behave in some special way. And there are many interesting applications in matching markets like Uber, Airbnb, and I've heard a very funny example of this in some TED talk about dating site, but I think I will tell if I will have time at the end, I will tell about that. Okay, so when we have this equilibrium, the next problem, and I think it started in the 90s, is equilibrium computation. So when you have a really big game, then computation of Nash equilibrium is, well, pure Nash equilibrium can not exist. So it's an NP hard problem, NP complete problem, I think. And for the mixed strategy next Nash equilibrium, Papadimitriou proposed, and others proposed the PPAD class, special class, for the games where you know the solution exists, but you need to find it. And it still remains a difficult problem how to calculate in general Nash equilibrium. But if you have some refinement, then it's much easier. For example, correlated equilibrium is just linear programming, and so some even easier. And also to make some connections and lines with the topic of this school, it's a learning algorithm. They also have some relation with game theory. For example, regret minimization and fictitious play and replicative dynamics, they are actually occurring in game theory problems. And then they start to go further. Now they applied in the different schemes. So when you have, as I understand it, as I'm understanding this, that when you have, for example, reinforcement learning, you can imagine that environment is just some environment, and you just communicate with the environment. But if you, for example, know that there are different agents in this environment and they are also learning, and you know something about the structures, then you can use it and learn fast. Okay. So when you have, the problem is that actually I strongly recommend you recent school in Tübingen, where Konstantinos Dalakis, I think, he presented quite a long lecture about game theory and machine learning game theory and machine learning, mainly from machine learning perspectives. And he tells about situation where you have very simple game where you can calculate equilibrium very easily, but you can't actually, when you launch learning process, then you have go into infinity. I mean, you just have oscillations that go to infinity. And he found some conditions and improvements how to fix this. But for very simple games, from difficult games, it's still open. So when it's a map of game theory, and I will mainly follow it when I prepare this lecture, and I think so. Game theory, and there are three main like classical topic. Behavioral game theory is a little bit out of game theory because it's about experiments. It's about situation where people, real people, do not behave as they expected by game theory. It's really interesting because it's like helps theory move, and I will tell about, but very little. So if you have classical game theory, then you have two big branches: is a complete information game and the incomplete information game. So information is crucial because depending on information, you can have very different solutions. So incomplete information game, you have everything about other player, everything about their moves usually, and about game structure and so on. But if it's simultaneous games, then you don't have the exact moves of the other player, but you have everything about payoffs, about game structure, and so on. So in static simultaneous game, you have usually it's one move game. So it's like you made a move, and simultaneously other player make move, and you see the result. Dynamic sequential moves, it's when you have a tree. It's a chess, basically. So you have one person moving, second person moving, and one, a third, and so on. Incomplete information game is where the fun begins because it's usually Bayesian games. You know about Bayesian, I think, learning and modeling already, but in games it's also very important. John Harsanyi, who got the Nobel Prize, he showed that any game of incomplete information can be transformed in game of imperfect information using special Bayesian strategies. And we have a static game where you have Bayesian Nash equilibrium, and you have dynamic game where you have perfect Bayesian Nash equilibrium. Also another, I mean, now it's very important also topic is the algorithmic game theory. It's how to calculate actual equilibrium, or how to calculate the game if you have very big game and you can just formalize it with this simple matrix, or matrix is very big, for example. What you do in this situation. So algorithmic game theory is recent topic. Okay. So still, when we say about game as a mathematical object, I mean, if you have a mathematical side of game theory, it's not only experiments, it's not only strategic situation, but it's also mathematical object. And to define a game, we need to define set of players, set of strategies, and payoffs. And it's very simple to write down, but it's really difficult in the real world. For example, for chess, we can write down set of players, but we can't write set of strategies at all. And if you have real situation, you can also, for example, can you write down every player who will influence you tomorrow? Sometimes it's just not possible. Okay, so why it's important? Why it is important to understand game theory as a strategic situation, and how we can understand what happened if you do not do this. Well, there is a funny stories. I like stories about game theory especially, and they called Cobra effect. And there is a Wikipedia article, we can read it about Cobra effect, but I just make some simple notions. Not everyone. If you're interested, maybe you can ask me in the questions. So what is Cobra effect? It's when you have a game as a strategic interaction of rational players who want to maximize their payoffs, and you do not do not take into account their possible actions. So you don't take into account what is better for them. And the like iconic example of this is India, when it was under the British government rule. It was like 300 years ago or something. And at some summer, there happens to be many cobras. And as usual for British, as they do with wolves, for example, they just sign the the reward money for the head of snake. Okay, and after some time it was quite good because people bring them the head of snakes. But then British realized that the locals, they just start to how you get, they just start to raise cobras at homes, so just to make money. And British were a little bit angry about that, so they announced that from sometimes they just stop any payment. And what locals did, they just released the cobras to the wild, because it was like okay with the picture of the world. So the result was opposite what the British tried to achieve. And the situation where you can you create some incentive for people, but they behave not the way that you want, but they behave in the way they found the most the most good for them. And exactly this story is an anecdote that never happened actually. It was imagined by some British sociologist, but the situation is he caught it is very real, because many real situations that looks like this really happened in different situations. I recently read about almost the same about wolves in Russia like 200 years ago, where the peasants start to create wolf tails from just some materials, because they killed all wolves, and but they wanted money for the tails. Okay, so when we speak about application of game theory, it's very wide, actually very wide field. From the beginning, naturally, it was mainly economy application. Yeah, so it's looking for find the equilibrium, understanding how works duopoly and oligopoly in price wars and something, models of negotiation, contracts, auctions, how to create auctions, allocation of public goods. It's also topic of mechanism design, and matching algorithms. It's also very nice economy application. When we speak about social science, it's different social dilemmas, how to understand the why people behave in that way. It's for example free rider problem, some dilemmas about prisoner dilemma, and like it's ultimatum game, dictator and trust games, also how people behave in different situations. Ultimatum game is very actually in I found it not every day, but very frequently in the real world. Voting system are also part of game theory, because when you have voting, then you have players, it's voters, and you have some rules, it's a system, and you have some strategic negotiation when, the best probably, I mean, when the voting system is created, the creators of this system, they expect that people will do sincerely voting. So they just vote for the guy who they found the best. But in reality, it's always a compromise, and you vote not for the guy you want best, but for more frequently, you vote that some other guy who you think worst will not be elected. So, and it's a manipulation game. So, and the main problem is how to create a voting system which will be free of manipulation and will be good in some sense, free of some paradoxes and so on. And spoiler, it's not possible. Okay, and the last interesting application is the coalition and power indexes. It's how to measure the power of different members of coalition. When you have, for example, coalition, it's actually almost the same side as a non-cooperative game. A game also divided in cooperative game and non-cooperative game. And then you have cooperative game. It's a situation when players should create coalition and then agree how to divide the profit inside the coalition. And this is a coalition of games and how to measure the importance of every member of this coalition. Biology, very interesting topic. It was mainly due to John Maynard Smith, but other biologists as well. And he applied game theory to evolutionary process and found that many situations in real life, they can be described by game theory models. Especially it's evolutionary stable strategies which form special Nash equilibrium and replication dynamics when you have like a game of evolution where if you won you can replicate your genes to your siblings, and if you fail then you just die. And in this situation, replication dynamic, how this how some strategy can win in this game. It's closely connected with learning models and how some algorithm can learn in some situation. And least but obviously not last but not least, obviously it's computer science, and there are many different applications. They are launching, exploding from everywhere, and start from network routing, and some routing games, how to understand protocols and how they work when they try to conflict with each other. It's auctions, especially combinatorial auctions in the internet. For example, eBay auctions also. It's topic of analysis. Matching algorithms. It's also very interesting topic, how to match set of customers to the set of buyers and sellers, for example, and how to do it quickly and efficient. And well, in reinforcement learning, I said some word about that. And in this lecture of the Skalakis in Tübingen, you can read about GAN, generative adversarial networks, and how they form the game when they play, and how they approach to equilibrium in this game. So it's also interesting hot topic of game theory. So my point is that if you want to apply these algorithms, then it's better if you understand the ideas of the core game theory and how they evolve, how they were created, how they evolve, how they work in a human environment, and then you will understand better the ideas and the concepts of game theory, and you can apply them in any field of research you want. Nobel Prize in economy. In game theory, there are five Nobel Prize. It was like golden century or something, golden decade from 1994 for 2012, where Lloyd Shapley and Alvin Roth, they got Nobel Prize for matching algorithms. Alvin Roth actually applied matching algorithms to the kidney exchange, and it was really fascinating topic. How one algorithm can save up to I think 100,000 lives a year in America. So now I talk a lot, but now I want to make some feedback. So right now we will play a game. I will send you a link in a Slack on the Google form, and I will do it later. First, I will explain the rules of the game, so we have like all understanding, no misunderstanding. So game is very simple. We will play, I think, 4 of this game, and you need to choose an integer from 1 to 100. When you, after you choose the integer, after that, when I gather all the numbers, I calculate the average of this, and then I take 2/3 of this average. You see, 2/3 of this average, and player whose number is closest to this 2/3 of the average is the winner. If you know this game, try to win it. If you already playing this game, for example, you can think about how other people thinking, and even if you don't know this game, you also you understand. Yes, if you have any questions, you can write them in Slack, for example. So your choice is influencing the outcome of others, and their choice actually change your outcome. So to choose the number, you need to understand how other person will think, and uh, and how they what number they will. Okay, so now I will copy first link in game theory Slack. Let's try to do it like in 3-4 minutes. Not think, please, not think too long. Also, it's a good it's a good measure how many people actually listen. It's 22 for now. It's 36. Okay, cool. So do you need more time? Okay, let's another minute, since answers keep coming. So Okay, so it's 74, 75. Okay, I will wait 10 seconds from the last increment to be sure that nobody. Um, uh, Unfortunately, I don't have like feedback, so I don't know how many person actually wants to vote. Maybe organizers can ask in YouTube. Because I don't want to, I need to close the form, but I don't want to that some listeners do not do not send. Okay. $80. No. Okay, but only 81 or only send. But okay, it's fine. I think I will close now so we can proceed to the lecture. Okay, so um, give me some. Give me a few seconds. Give me a few seconds. Okay, so I have result, but before this result, I want to speak about little bit about. So I have a questions. I have a couple of questions. Does anyone choose 100? How do you think? Well, I obviously I can't ask you directly, but actually, yes, some people choose 100. Does anyone choose more than 66? Why 66? It will be explained a bit later, but yes. Does anyone choose one? Yeah, some number of people choose one. So, and the last question, are people rational? So, obviously, the person who chose 100 didn't want to win. Yes? Or they all probably probably it's possible that he or she didn't understand the condition properly, but more reliable version is that maybe he or she just want to have some fun. Okay, and you can think that it's not rational, but in sense of game theory it actually is, because rationality in game theory is two things actually. First, players make decisions based on some maximizing utility function. So they try to maximize some utility with mild assumption about ordering, for example, like transitivity. If you want apple more than banana, and you want banana more than orange, then you want apple more than orange. Should be. So it's transitivity. If you have a couple of axioms, it's called Neyman-Morgenstern system of axioms, then you will always have utility function. But rationality also includes other assumptions that players are capable to calculate their best strategy. So the phrase that rationality means that players maximize the utility function means that they can actually calculate this maximum. But in reality, people do not calculate maximum, usually. Good. So, for example, if you have two actions, you have two actions, and you can choose one of these two actions, first action or second action. Think carefully. What action will you choose? How do you think? What is rational? Choose action 1 or choose action 2? Well, if you're first player, you're first player and you need to choose one action. Sorry about that. So, rational is to choose action 2 because 5 is bigger than 1, and if you're rational, you only consider your own preferences. You don't include, well, if you specially formulate games this way, that you will include other outcomes of other player in your preferences. You can do this, but this must be expressed in your preferences. So if you care about what other person take more than what you take, then you need change your preferences here, and then game will change. So in this game, rational player will always choose action 2. Okay. So this is a slide from TED presentation of Dan Ariely about are people rational, or about rationality. He actually very famous investigator of rationality and irrationality, and how people actually make some irrational things. And this is the after death organ transplantation consent rate of by different countries. So here we have Denmark, Netherlands, United Kingdom, Germany, and here we have Austria, Belgium, France. But wait a minute, Austria and Germany, they are culturally and very close, and Belgium and Netherlands, if you not live there, you probably will be hard to distinguish. And why the rate are why the difference is so big? Well, some of you know the answer, and the answer is that in this country there is in effect explicit consent, and here it's presumed consent. So here you need explicitly agree to to give you organs for someone after your death, and here you must explicitly refuse in this country. And this makes difference. Why? Well, because it's difficult problem. If you ask this question on the street, some person, he will find it difficult to answer immediately, because it's like a very important matter. So people usually do not answer this. And when they do not answer this, when government make legislation, laws, here they made explicit consent and they got these numbers. Here they made presumed consent, they got these numbers. But this is not rational in terms of game theory, because if you do not want to do this, it's okay. And if you want to do this, it's also okay. But you can't sometimes you agree, sometimes you don't agree. Depends on legislation, of the rules. Okay. So actually, when you read a little bit, I read a paper that this number a little bit exaggregated for the TED talk. It's understandable. So it's in reality these numbers are less than 99%, but the difference is exists. So this is Dan Ariely, and I surely recommend his books if you want to understand the irrationality of people. And one of his funny experiments is he found this on Economist page someday, when you can, sorry for a little bit blurry image. So you can here you can get Economist subscription to Economist.com for $59. Here you can have print subscription for $125, and here you can achieve print and web subscription for $125, the same. And firstly, he thought, what a stupid idea. Why do you want this? It's obviously better, yes. And this is actually a trap. Here, it's a marketologists use a lot, and I think it's if you read Kahneman, Thinking Fast and Slow, it's some idea of this also explained in the book. So when he give it to his students, he got this result: 60% choose this, 84% choose this, and 0% choose this. So if people rational, then suppose we remove choice that nobody wants, then their preferences should not change. But when he actually removes the middle line, middle possibility, then now 68% wants to get subscription and only 32% wants to print and web subscription. So this is how easily manipulate people if they don't aware. So if they don't understand what is going on. So it's wow. This is when rationality of game theory is not compatible with rationality of our everyday life decisions. So back to the game. Actually, you have well, the winning number is 23. So I failed. 22 and 9. This is the winning number. 22 and 9. So you are like smarter than I thought. And the winner is someone who named 23. If there is one, I will try to. Yeah, it's Nellis. Nellis named 23, and this is the best possible. Oh, yeah. Someone very smart named 18 and a half, and I think it's not. Yeah, but it's changed a little bit, but not much. Okay, so Nellis is the winner, and what we can learn from this game? Well, we can learn the idea. Okay, but we will play this game again after I explain the idea, so you can participate later. Okay, so first there is two very important ideas which form, I think, two of the most influenced ideas in game theory, maybe not most, but very influential. First idea is dominant and dominated strategy. So what is dominated strategy? We can think this way about the game we just played. If everyone choose 100, it's not likely, but it's not impossible. I mean, it's not forbidden by the rules. So it's like maybe plausible, but yeah, in reality, it never happens. Then the winner move is 66. But since situation when everyone chooses 100 will never happen, this means that your winner move would be less than 66. So it's not possible to win theoretically if you choose numbers bigger than 66. So everyone who choose numbers bigger than 66, they actually didn't read the rules of the game carefully. So they're not rational in game theory sense. So choosing number bigger than 66 is not rational at all. It's dominated strategy because it cannot win never. So if you're rational, you can think why I should play strategy that I have no chances of win whatever whenever. So you can remove from the consideration all strategies bigger than 66. And if you understand this, and you understand that everyone other also understands this, you can remove the 66 from the consideration of any possible player. If you think the player, of course, rational, but this is the idea. Then, if you remove every strategy bigger than 66, you can say, now it's not winning move to play strategy something bigger than 44. So you remove everything more than 44. And continuing this ad infinitum, you come to very confusing conclusion. Everyone should choose one, and then everyone wins. But from my, I think, close to 50 games that I played with people, not a single one, all people choose one. Okay, but yeah, it's just first game. So this is first idea. You remove dominated strategy. If you found some strategy that is better than any other strategy, it's called dominant strategy, then you will play it. And this is a choice of rational player. Second idea, it's the best response. There's another line of reasoning, and I think the spike in 33, I need to check, but I think it's, no. Yeah, so let me move back and show you the distribution. So this is the distribution of your votes. You see it, yeah? So we have 5 persons who named 1, and we have many persons who named 22. They also, I think, know about game theory. And we have 4 persons who named 33, and well, 50, I don't know why, 50 have no chances actually, but okay. And yeah, so 33 is a natural choice. Why? Because if everyone choose random uniform numbers, you don't know anything about distribution, think it is uniform. So average will be 50, and 2/3 from there. That's why people call, I think, 50, because the average is 50, but they just forgot about 2/3 maybe. So the winning number is 33, and this is the best response to the belief that everyone choose numbers at random. It's actually a starting point for a fictitious play learning algorithm, where you have some unknown game and you have some players, and you launch the learning process as following. You start with some random distribution of other players' strategies, and then you start to make best response for this distribution, look for best response and play this best response, and then you play best response to the previous step strategy of other player. And this ways, if you have like the only Nash equilibrium, in many cases you can converge to the equilibrium. So play best response to your beliefs. First level of beliefs, if all chosen random, then best response is 33. Second level of beliefs is if everyone do first level, then they all choose 33, and the best response will be 22. That's why 22 was like spike, yeah? Because 22 is the best response to 33, and 33 is the best response to the some average random belief. Third level, if all choose 22, the best response is 11. And continuing this, we will come to the very interesting idea, the same as the previous one. The 1 is best response to believe that everyone play 1. So everyone wins in this solution. They just should understand that playing 1 is the best way, but they didn't. Yeah, because it's always some mistakes, errors, some misunderstanding, and there are also players who doesn't want to win, who just want to make fun, maybe of you. And it's also rational, but just their rationality is different from your rationality. And in real life, you need to take into account these players also. That's why it's so difficult to apply a general theoretical framework to the real life. So this idea that everyone understands that 1 is the best choice and everyone knows. For example, imagine that we play for real money. Then probably the numbers of players who wants just to make fun will be reduced to a 0 if you play for your money, for example. For example, everyone pay like $1, and then everyone who wins shares the whole sum between them. So the best way is to choose 1 and always get your $1 back. And yeah. So, and this situation where you know that they know that you know that they know it, and infinitum is called common knowledge. And it's also an important concept in game theory. So that's why how we can play an equilibrium, where we know that this is an equilibrium and they know that this is an equilibrium. And the best explanation of common knowledge idea that I read, it's a joke. I think it's time for joke because we're just too much talking, I think. So 3 mathematicians came to the bar and barman asks, do you all want beer? And first mathematician said, I don't know. And second say, I don't know. And third mathematician said, yes. So yeah, that was a joke, but yeah, I obviously can't understand is it good or not. Okay, so this is the result of, I think, 5,000 participants in made by site waitbutwhy.com, and they play this game, and they actually, well, they start from 0, we start from 1, it's a little bit different. So we have, you see, we have many people who named, it's 5,000, so 12% of 5,000 is a couple of hundreds, they name 0 and 1, so they know about this game, and they like smart but poor because they didn't win. And actually here the 24 numbers was winning numbers. So number. I recently read about interesting paper about application of this game to understanding how crypto traders work in their like so they also try to substantiate hypothesis that better trader will be better in this guessing game. So this was the idea, because it's very close to the process that you need to understand what the other people understand, but better to be one step ahead of the majority of other people. So now you know everything about this game. You know the equilibrium. You know the common knowledge. You know the best strategy, or equilibrium strategy, not the best probably, because that doesn't win. So let's play this game again. And think carefully. How do you think? What number will win this time? I will send you a link in a second. Okay, let's give you like 5 minutes, okay? So everyone can make your choice. Actually, actually you can cheat, but please don't do that. I mean, you can send 2 or 3 or 5 different numbers, but we don't have time for authorization. So please just don't spoil the game for everyone. Okay, I rely on your fairness. So far, 91 answers. So, and not increasing. So I think everyone who wants to make their decision, they already sent. Okay, so I close the form. Okay. Okay, let's see. Let's see. All not integer numbers would be ruthlessly rounded to the closest integer. Mm-hmm. So, final result is 8.22. 8.22, so 8 is the winner, and we have a number of winners. I found 2. Oh, no, sorry. So, yeah. So we have Mikhailo, Alisa, and Alexander. And they are, and Pedro Pinheiro and Eduard. So we have a lot of winners. So everyone who named 8 is a winner. So as you see, this is what's called bounded rationality process. So when you don't have ideal rationality of game theory in real life, but you have bounded rationality where people learn, actually human learns from the game and they try to improve. Even if someone named 100 and also some people, they named like big numbers just to increase this average, but the majority named 1, but naming 1 is like too obvious. Yeah, it's you can't win with such an obvious strategy. So the bounded rationality is when you approach to equilibrium slowly or faster, depends of your like conditions. So this game actually have unique Nash equilibrium and everyone named 1. And if we play many times with like real wages, then I think we will came to this idea. So now I want to little bit summarize the idea of dominance solvable games. So this class of games that we played, it's dominance solvable games where you have dominated strategies and dominant strategies. So dominant strategy is a strategy that is best than any other for you. So it gives you better payoff for any possible strategies of other player, bigger or equal, and bigger at least in one case. So it's a domination definition, and if you have strict domination, then you must be bigger, strictly better than any other. And dominated strategy is a strategy that is worse than some other. So if it's worse than some other strategies, then rational player will never play dominated strategy and always play dominant strategy if one exists. Now I think it's the end of our first part. Yes, yeah. So I want to give you one small problem to solve, and we can start with the solution. It's relatively easy, but it's beautiful this idea of dominance. It's give you nice explanation what is going on. It's also connected somehow to reality. So we have 5 players, A, B, C, D, E, and each of them has 2 strategies: use car, own car, or use bus. And when they use car, they pay different price. I mean, so their payoff is -1, -3, -5, -7, -8. It's not exactly the price of using the car, but maybe some sidelines also utilities like I don't want to use my car, or maybe I have old car and so on. And if they use bus, then the price for each passenger depends on the number of passengers in the bus. So if only 1 passenger uses the bus, he pays 10. If 2 passengers, they pays 8 each. If 3 passengers, then they pay 6 each. If 4 passengers, they pay 4 each. And if everyone use the bus, they pay each $2. Okay, so let's just solve and find the equilibrium of this game. Yeah, because I close the doc because we have like time window for the game, because I need to announce the result. I can't just keep it open for all time. It's just short game. Sorry if you don't do the choice. It's okay, because it's a generally game for understanding. So you can learn from the how other people actually make decisions, even if you don't make the decision. And also we have 2 games to come on the next session, so please pay attention, because to announce, I mean, to proceed the lecture, I need to announce the result, and to announce the result, I need to gather answers. So I can just wait for the end of the lecture. Okay, now I will see the questions. Okay. Okay. So what I do, I just wait for the questions, or I just answer. Okay. I can do this. I can show distribution right now. Actually, I can share the result if you want. It's just Excel tables. They are stored. So if you want, just indicate me. So this is the distribution from your last. You see, 196, 44. 30, but yes, this is big margin, and 33 still. Okay, so we have 11. It's actually a good choice. I think it's close to the 8. We have 8, yeah, 5 winners, 8, and we have 26 who named 1. Well, I think it's okay if you just solve and write down your answer, and I will announce it after the break. I mean, I'll show the solution. So you just check yourself. I think it's the best. I have some problems that I can give you at the end of the next session, so you can just solve it at the evening if you want. Okay, so reinforcement learning background and multi-agent RL. Yes, there is a connection, of course, but to get, well, to use as far as I know, the results of game theory are using to prove the existence of solution, or maybe existence of equilibrium for some special class of algorithms. So when you have a concrete problem and you have concrete algorithms, the difficulty of this algorithms, they are just overcome all other things. So you just like fight with algorithm, fight with concrete problem. And if you formulate it in a game theory setup, you will get some maybe concise, small formulation, but you can just solve it so directly. So I think that you can use it, obviously, but for example, for simple problems at least. But if you have concrete problem, then probably use general method of game theory is not best. Maybe heuristics works better, I think. Do we assume that everyone treats the game seriously and play competitively? Yeah, well, it depends on the game. Of course, actually, the problem with the problem with game theory is that the naming is not best. I mean, when you say I'm working in game theory field, then younger generation said, oh, it's computer games, it's fine. And older generation say that something not really serious. There is always special term as serious games, serious gaming, just to underline that this is not just games. But when you have real situation, yeah, you must include into account what real humans or persons can do, and this way you can just use ideal construction of game theory to predict the outcome. So this is also interesting idea that you know that if you work in artificial intelligence field and you ask when they create the general artificial intelligence, the closer person to the field of artificial intelligence, then the less confident that it is possible he or she is. So if you know well about artificial intelligence and some guys ask, hey, you're about to create some Terminator and he will destroy all humanity, and you know that it's just algorithms, it's funny question for you. But if you don't know anything about it, then it's for you plausible that next year some Skynet will take control over the Earth. But so in game theory, there's similar situations that the more you know about game theory, the less optimistic you're about practical implementation. So you know that some implementations are good, some implementations are really working, but in general, people do not behave in the way that game theory predicts. So game theory, you can use game theory to, to provide ideal solution and to understand how to, is it possible to converge to this ideal solution. So it's in the chess, you know that right now, grandmasters in chess do not play with computers anymore because it's pointless. It's just computer is like 1,000 points rating bigger than the strongest of humans. So you don't play computer with chess. But if two ideal chess programs play with each other, they play some moves and you don't even understand these moves. So you see the solution, but you can't actually use it for your real life. It's something similar with game theory. You see you formalize the situation, you calculate the equilibrium, but then you start to think how I can use it, how I can use this equilibrium notion in my real life. And sometimes it's not possible. Question of last problem. How do you think who will travel by car and who will travel by bus if the people are rational? This is the question of the problem. Yeah. So yeah, I answered. Yeah, right. If player A goes by car, he pays 1, B pays 3, C plays D is 5, D plays 7, and E pays 9. Yeah. And if they go by bus, then if everyone go by bus, then everyone pays 2. By each person pays 2. Well, I will prepare some links and books for the, I think, tomorrow lecture, where I will tell about Bayesian games and some applications. So I will just summarize all links together. Right now, I can recommend you to find this lecture of in Tübingen. I just show you. So it's game theory machine learning. So you can find this, yeah, Konstantinos Daskalakis, Tübingen this year, actually it was like months ago, game theory in machine learning. It's like special, but quite special lecture, but it's from point of view of machine learning specialists and how to use the game theory in the in machine learning in guns especially and different other problems. Okay, I think you. In clinical trials, well, you see, to have game theory working, you need to have conflicting agents. So, and with some like meaningful strategies. I think that just Bayesian modeling or just Bayesian models makes more sense in classical trials, just because, well, game theory is a little bit over, I think, over too much. But yeah, I remember one funny application. I read a book about game theory and data science, and they also use game theory to get information about surveys. So if you have some survey and you pay money for people to fulfill this survey, sometimes you can get this situation where the same person just make many surveys. So you need to create special incentive mechanism so you can encourage person who make all survey seriously and punish person who just put some check boxes and without any thinking. So you create a special mechanism. It's a mechanism design problem. How to create incentive for people to work good. So this is how to create this mechanism and how to measure the working. It's a game theory problem. So yeah, and about this application. So since game theory is about strategic decision making, you can find very unexpected applications. So maybe in clinical, I didn't hear about clinical trials application, but it's maybe possible if you have some strategic situation. For example, I told about data insight. So they create a data insight, and firstly they create like unlimited connects, and you can spend these connects to approach to some person you want to meet, and it wasn't working good. It wasn't working good, and then they found the idea that they invite the economist, and he proposed to make this connects deficit or sparse resource. So he proposed to give every person only some small, like 30 connects per month, and when they get this when they create this change, the data inside starts to work. Because now, if some person receives the connects, he or she knew that this connect is actually quite important, and you can't just buy it. You have like limited amount per month. So so the two implications. First, the persons who are looking for the partner, they start to look seriously about some profiles, activities, interests. They try to find better match, and the persons who receive connect, they understand that this is quite difficult to get more. It's impossible to get more, so this connect is quite valuable. So maybe I should respond, and so this is create bigger market or better market for them. Well, actually, I did a couple of popular lectures about voting game theory and about different system of voting. And as you know, we have new system now. Actually, in Ukraine, we have new system every election, I think. Maybe I can remember 1 or 2 elections that was performed under the same system. So it's a constant change and always unexpected, of course. So a new system is so difficult. So you need specially learn about this and model, because it's something like transferable vote, but I don't know how it will work, because not only the system should be analyzed very carefully, but also the people who will perform these elections under this system. So I think that actually this system would be push for new parties. I mean, before this, we have local region parties who were strong in this particular region, and they do not have incentives to unite with any other, because they have everything they want. But now they will be punished by this new election system. They will be punished if they do not get enough votes in all Ukraine, and there's some rules how you need to have some candidates in more than some percentage of regions. So they just launch the process of unification of different local parties in one new big party, and I think that it will be the case. Yeah. So yeah, we have first answer of the problem. Yeah, this is non-cooperative game, so we assume that they cannot make agreements or negotiation or pay each other. Everyone choose its own decision independently and try to maximize his own utility. Yeah, there are. I know there are a lot of ways how to improve this game, but I'm asking about this particular game. Share problem to the Slack. How I can do it? Maybe someone can make screenshot and do this, because I have Slack on my iPad and I can't right now switch. So if someone can make screenshot of this problem and send to Slack, I would be grateful. Oh yeah, it's an interesting question in Slack. So in our previous game, if everyone choose 100 and everyone wins, is this the same situation when everyone choose 1 and everyone wins? Well, the point of equilibrium, and I will give you definition a little bit later, but the point of equilibrium is that this is a two principal different situations. When you have everyone named 1 and one person named 3 or 4 or 5 or any number, this person who deviates will lose. If everyone will choose 100 and one person will deviate to 66, this one person will win. So everyone named 1 is an equilibrium and everyone named 100 is not an equilibrium. It's also possible profile, I mean, in the game, but it's not the equilibrium. Okay. So I think we can rest a little bit. It's you know, Zoom allows you to make a virtual background. It's a big library, I think is in Amsterdam. It's nice background. Okay, so I need the rest because next lecture will start in like 20 minutes, yes? So, okay. So what we will do now, rest a little bit for 20 minutes. Ah, no, not 20. Not 20. What is the timeline? Can you remind me, please?
It's 12:30 in Ukraine.
So we just disconnect and rest for a little bit, yes?
No, you should not disconnect. You just can turn off the camera.
Yeah.
And, yes,
so
yes.
It's 1 p.m. 1 p.m. is the start of next topic.
Okay. Okay. Yes. Okay.
Okay. Bye.
Bye.
Okay. So we are continuing our lecture. So I saw some correct answers. Let's try to solve this game. And well, I just use annotation here. Obviously, we have, okay, it's actually a good exercise how to formalize the game. So we have 5 players, yes, and we have two strategies for each: use car or use bus. So we have like big matrix, but we can't actually draw this matrix like if you, for example, we have 2 persons, we can draw matrix like this. We can here use car or bus, yeah, car, bus, and then we can write payoffs here. So it would be 2 numbers. Usually one number is connected to this player and one number is connected to this player. So usually they write this. So for example, we have D and E. Okay. So if they both use, it's a little bit not that simple, but so if they both use car, they pay like 7 and 9. If one of them use car, he pays the same amount as the one who pays who use bus. I mean, right now I simplified this game for only 2 players. Forget about ABC. Just want to construct the matrix of this game. So here we have 7 and 10. And if they both use bus, they pay 8, 8. Okay. So this is called matrix or strategic or normal form of the game. And the main characteristic is that players make their decisions simultaneously. So they do not observe the choice of other player. They make it at the same moment. So what is the good strategy for player D? Well, if player E plays car, then, and remember these numbers, it's what he pays. So we want to minimize it actually. So if player E use car, then 7 is better than 10. And if player E use bus, then 7 is better than 8. So this means that this is dominant strategy for player D. Now consider the situation for player E. If player D use car, then 9 is better than 10. Yeah, so it's like best response. And if player D use B, then 8 is better than 9. It's less pain. Okay. So we have situation where player D has a dominant strategy. Playing use car gives him always better pair. So rational player will always play dominant strategy, and this means that we can just remove this strategy from the consideration. And after we remove the strategy from consideration, it happens to be that player E now also has dominant strategy. It's use car. So if you have only 2 players, D and E, it is rational for them to play car. And this is an equilibrium. So you get the idea. If one player has dominant strategy, then he will play it. If some player has dominated strategy, he will not play it. And removing strategies, we receive new game, and then we analyze it. So now we have 5 players. Suppose that some of them use bus and some of them use car. Let's consider payoff of player A for different situations. So we have only payoff of player A. So we have A here, and he can use car or use bus. And if nobody, we will put here nobody use car. So 0 using bus, then his payoff would be 10 and 1, and the less is better. If only 1 use bus, then it would be 8 and 1. If 2 use bus, then it would be 6 and 1, and 3 and 4, 1, 4, 1, 2. And put in this way, we immediately found that player A has a dominant strategy. The strategy that gives him always better payoff. It's always use car. Always use car. So player A will never use bus. Knowing this, we can now draw the same payoffs for player B. So now, if player B use car, if player B use bus, if 0, 1, 2, and 3, and I will never use bus, so it's 4 using bus is out of consideration. So he has 3, 10, 3, 8, 3, 6, and 3, 4. And now, only now, player B also has a dominant strategy. Because before we remove strategy for player A, player B doesn't have a dominant strategy, because there was a situation where he gets 3 here and 2 here if everyone use bus. But since we know that I will never use bus, we came to conclusion that B will also never will use bus. And continuing this way, we can draw all this matrix. We came to conclusion that no one will use bus. Everyone will use their own car. And surprisingly, when I posed this problem on my Facebook, it was a long conversation, debates, what we can do about this and how it's possible. Because when they all use a bus, they pay $10, yes, to each. And when they all use car, they pay 10 plus 5, they play 25. So it's obviously worst choice for the society, yes, when everyone use car. So what we can do, we can pay something for A for his convenience. And the point is that when you have multi-agent system and every agent just trying to increase their own payoff, their own utility, and it's big system, very small changes in rules can create very big outcome. It's called emergence. So if you have emergent system, when you have multi-agent system where small changes in rules of interaction can create big response of the whole system. And the best actually illustration for this is a Thomas Schelling segregation model about how people segregated in American cities by districts, and Schelling shows that there is a multi-agent model which can explain why it's the case, even if I mean rules are quite changes in rules are quite small, but this can create a big response after some time, because every agent actually do something by itself, and when they gather in some like system, it's big change. Okay, so maybe we can just kill player A, no A, no problem, or burn his car. It's also possible. So then if A is not in the system, then everyone will use bus. It's better. This process is just don't start of elimination of so, and there is actually a nice acronym for this. It's EIEDS. Iterative elimination of dominated strategies. And the equilibrium that we get in the result called the equilibrium obtained by EIEDS. So now we came to the Nash. Nash was very prominent also scientist, and you can know something about it from Beautiful Mind movie. I will I will give you a link for some small piece where Nash understands the idea of an equilibrium. But my point is that not mine, but many game series that they actually mess with the idea of an equilibrium, and it will be your task for evening to see this small part on YouTube and understand why it's not in equilibrium. So notion of Nash equilibrium is one of the most influential and important in game theory. And you know that maybe that Nash, when he came from school, I mean, he get diploma, magister diploma, and he worked like for 2 years and write in game theory. He wrote 4 papers, and 2 of these papers is like student one paper or small works. So, but the idea wasn't so influential that and then he get schizophrenia. Yes, and he fight all his life, get better, get worse. And in 1994, he gets Nobel Prize. So what is the Nash equilibrium? Suppose we have strategic situation like we had in our game, or we had in this car and bus problem. What rational player should do? What action player can choose if he wants to maximize his payoffs? Well, obvious answer is the best available action. But outcome for player depends of action of others. So each player must form a belief about other players' action and preferences. So should be best available action, and each player form belief, but player can't make choice alone. So they can make, and then in non-cooperative games, they can make forced contracts. It's actually a field of cooperative game where players can create what is called binding agreement. So they make agreement to work together, providing that they make division of the future payoff. And the main point or problem which is considered by cooperative game is how to propose division which is suitable for everyone, so they can like make this binding agreement, and then everyone gets like fair share. So it's a notion of fairness in cooperative game theory is quite important. It's Shapley value and other core and other things. So Nash equilibrium, basically turning to the point, Nash equilibrium is a strategy profile when no player can increase its payoff by unilateral deviation from the profile. So remember our number game. When everyone name 100, in this profile everyone wins because they have the same distance to the winning number. But if one player deviates, he gets all to himself. So he will win if he will deviate. If everyone names 1, then player who deviates lose. And this is a difference between equilibrium and not equilibrium. So equilibrium is a strategy profile or point of the game where no player can increase his payoff. And it's important that they deviate by one. So they can deviate together. So this is the main difference. It's like if you imagine local, for example, you have ball, yeah, in some potential hole, yeah, and you have better hole here, so ball wants to go here maybe, but no effort of one player enough to get him here. So local minimum, it's like maybe best illustration of what is Nash equilibrium with respect to the combined effort. So if we have a situation where no player separately can change the state of the system, so it's some sort of local minimum, then this is an equilibrium. There are different equilibria, and better one maybe, but this is the definition. Again, Nash equilibrium is the point where everyone gets maximum possible, providing that no combined effort allowed. Actually, Nash, it's young Nash here, and not so old von Neumann. I think, yeah, Neumann is the right pronunciation. Von Neumann, they actually meet in Princeton, and when Nash and Neumann was very proud about his minimax theorem. What is minimax theorem? I think you've heard about minimax method. It's a method to solve zero-sum games. So what is a zero-sum games? A zero-sum games is a special class of the games where if everyone wins, other guy should lose the same amount, or maybe other guys combined. So if you have two-player zero-sum games, then for every possible outcome, sum of the payoffs should be zero. That's why it's called zero-sum. It can be, so some of them are bigger. If one is bigger than zero, then other should be less than zero, or they can both be zero. But the point is that it's always zero. Sum is always zero. And what von Neumann understood, so how to solve zero-sum games? Well, this is an example. It's actually, in game theory, every small game is like famous for something, so there's a story behind it. And this game is called Bismarck Sea game. So we have like Second World War, and we have Japanese who wants to supply their troops, and we have American troops, and they want to bomb these Japanese troops. They supply it by the ships, so by sea. So if Japanese go to the north and American fly to the north, then they have 2 days of bombing of these troops. If Japanese go to south, south way is longer for 1 day. So if Japanese go to south, then American fly to the north, found that nobody is here, understands that they go to the south, and they go to the south and have 2 days of bombing. And if American go to the north and if American go to the south and Japanese go to the north, then American, like, they spend 1 day to understand that no Japanese on the south, so they fly to the north and have 1 day of bombing. But it's always at least 1 day of bombing. And if they understand that south, fly to south and Japanese go to the south, that it's -3 days of bombing. So how to solve this game? Well, actually you can solve it already. You know about dominant strategy, and you can see that the strategy south is dominated, weakly dominated for Japan, because you have -2, and here you have -1, -3. So this strategy gives worse payoff for this situation and the same for this situation. So this is a dominant strategy, flying to the north. And knowing this, for America, going to the north. And for America, flying to the north is actually also dominant strategy. So this is the equilibrium. But in general, zero-sum game, it's not so obvious. So minimax solution proposes the same. We start with finding minimum for Americans. Minimum, it's actually an algorithm. You can run it for general zero-sum game. So you found minimum by rows, and then you take maximum from this. And the same is for America. You take minimum, and then you take maximum from this. And if these two numbers have the same strategy profile, from the same strategy profile, then this is the saddle point. And the minimax theorem proved by von Neumann is that if you have mixed strategies, then every zero-sum game has a minimax solution. And he was very proud of this, but later Nash generalized this result, and when Nash showed von Neumann this his paper, he said it's so obvious that you shouldn't publish it because it's so obvious. But yeah, but Nash published. So what's the idea of Nash? We already talk about Nash equilibrium, but how to find it? Very simple procedure. I mean, for matrix game, you just need to mark best response for each player. So, for example, if Japan take this North strategy, then best response for America is 2. If they use this strategy, best response for America is South, and this is 3. And the same is for Japan. Here it's the same. Here the same payoffs, and here it's -1. So, and now we're looking for a profile which is best response for best response. And this is Nash equilibrium. Very simple. This way you can find Nash equilibrium in pure strategy if one exists. So I will want to give you one example of game. Well, I don't want me to play this right now because we have other stuff to do, but just think about it, please. So imagine that everyone has 100. Oh, I think I can make a poll in Slack, and you can answer inside to just not to flood everything. So the game is following. Everyone gets 100 provided by the organizers and a red button. So just imagine, please. If you don't press it, then you don't influence others. If you press it, then there are two effects. Every other player who didn't press lose $2, and every other who pressed lose only 1. And by pressing the button, you protect yourself from others in the same way. If someone presses, you lose 1 instead of 2. So this is the game. Each has 2 strategies, and this is actually happens for each pushing the button. So if, for example, if everyone pushes the button, then everyone will lose $1. If half of you press the button, then half of you lose $1, and half of you roughly lose $2. Okay. So I put it in Slack, and you can answer my question here by putting yes or no in comments. Just think for yourself. What do you want to do, and don't look on what others will do. So just think what you think is right or best way on equilibrium, or any rational suggestions what to do in this game. Okay. Is it clear? Oh, yeah. Oh, so now I should decipher this. Okay. So we have, yeah, press and not press. Okay, so I can actually go. I have a picture. What is going on? Yeah. So this is the most notorious and scary game in game theory, and it is called Prisoner's Dilemma. And I think it's the most famous one. Even if you don't know anything about game theory, I'm pretty sure that you heard about the Prisoner's Dilemma. So let's write payoff of each player. If nobody press a button, exactly one press button, exactly two press button, and so on. If you press button, you have here 100, 99, 98. If you don't press, then you have here 100, 98, 96. So pressing the button is weakly dominant strategy. Weakly because here they are equal for this. But so it's rational to press a button. Exactly rational. It just gives you more money always. Those who press button always get more money. But when I played this game in real life with real persons, it's almost always around division 60% by 40%. And 60% is those who press the button. So 60% press the button and 40% do not press the button. Why? Well, it's an interesting question because, well, actually from the beginning I thought that we have the same, almost the same situation, but now it's like 25. We have right now we have like 25% press the button and 75 press the button and 25 do not press the button. But it's fine because you are like in slightly different conditions than all others. But still, 25% do not press the button. And this is where game theory fails because people make decisions not only from consideration of imaginary payoff. I don't know. I never played for real money actually, so I don't know. But there is a bunch of experiments. I mean, I think the main researcher here is Colin Cameron. Colin Cameron wrote a book, Experimental Game Theory, and there is a lot of experiments for real money in this setup. So 40% is like altruism measure of society. So it's like 40% think that it is better to risk to get better for everyone than try to protect themselves. Maybe we can put it like this way. Because from the point of view of whole society, pressing the button is simply burning money. Yeah, you just burn money to make some insurance or protection from others. So it's like you can measure trust in some sense of this way. If you, I think, if you, of course, if there are some people from the internet you never saw this, it's much more easier to press the buttons than if you sitting in, for example, class with your friends and you know that it's not it's meaningful to press the button if you know that it's it's your share money, so it's money for you and you just burn it by pressing the button. But it's rational. So this is the prisoner's dilemma, and what is the problem with prisoner's dilemma? What is the story about this? Well, story about this. Actually, I make some disclaimer or something. It's not replayed here. It's not real game because in real game you should make choices independently and simultaneously. So you can't observe the choice of others. So it's not real game, but it's a setup. So, but even this setup shows that many people wants to and it's actually a good idea if you before this game, we said that all your answers are recorded, and we can create a list of altruists here. So this can also influence your decision. So it's not pure condition game, of course, but it's like example of interaction. So what is the story behind prisoner dilemma? I think it's quite common, but okay, I repeat it. So there are two criminals, and they are suspected in some big major crime, but they were caught for some very small crime, and the police, they put them in different rooms, cells, and asked to cooperate in exchange of I think probation term or something. So if you cooperate with your friend and you keep silent, then you go to jail for 1 year for this lesser crime you was taken. That police can prove. And if you deflect your friend or your criminal friend, then you go for free. It's just a probation, and he is going for 15 years. Actually, numbers are a little bit arbitrary. The most important that the condition should between these numbers should be the same. So it's 0 is bigger than -1, and if you deflect you tell everything, and he also deflect and tell everything, then you both get 10 years because you have you cooperate with the police, so you have some mild conditions. So what is the problem with this game? The problem with this game is that everyone wants to be here, yeah, because here is where they have only 1 year in jail. But deflection is a dominant strategy for both. So 0 is bigger than -1, it's better to go free, and -10 is better than -15. So put it in Nash equilibrium terms. If if the other guy cooperate, it is better for me to deflect always. Yeah. If the guy deflect, then it's also better for me to deflect. And the same is true for the other guy. So this is the best responses, and we have deflect is the best response for best response. So this is a Nash equilibrium, but it is inefficient because -10 is much worse than -1. So, and this is the problem. The problem that rationality demands you to deflect, but if you can assure that you will cooperate, then it would be better for both. So that's why some special rules are very common for criminal world, like mafia rules, when they try to avoid this prisoner dilemma. For example, there are many ways how to beat prisoner dilemma. You can make game repeated. You can add some other moves. You can change a little bit payoffs with some special add-ons to the game. But in original game, it's rational to deflect, of course. But if you, for example, you know that you can go out, but on next step, someone will find you and will kill you, then you will think twice, and maybe you will not deflect. So this is so prisoner dilemma is so important because it's actually very common in our everyday life. And if we start thinking about this, we will understand that it's actually you can start by I prepare one interesting example. Maybe you heard about this, is the brace paradox. So brace paradox comes from a routing game where you have, okay, so you have 100 of cars, and these cars are on this node. And they want cars, packets, people, anything, but let's keep cars. And they go from this sync node to this terminal node, and they have two possible roads. And these roads have different characteristics. So if you go here, its road is not good. This road is actually highway, good highway, and you spend 1 hour irrelevant to the number of cars going, because it's like capacity is much more than 100 cars. And here it's also, you spend 1 hour here and 1 hour here if you go by this link. But if you use this link, then the delay is proportional to the number of cars. So if, for example, if 100 cars go here, then delay is 1 hour. If only 50 cars goes here, then delay is 30 minutes, half an hour, and so on. So this game is symmetrical, so it's quite obvious that you have equilibrium where half cars go here, 50 cars go here, and 50 cars go here. It's very easy to understand that this is an equilibrium. For example, 50 cars go here, 50 cars go here, and if one car go from this line to this line, it's strategy actually. Strategy is choosing one line or other line. Then he will worsen his payoff. Payoff here is the delay. You want the minimum delay possible. And delay, if you calculate, is 1.5 hours. You spend half of hour here, 1 hour here, and or 1 hour here, half an hour here. And this is an equilibrium. Okay. So now we add here super fast one directional line. And this line has a 0 delay, like teleport. But we can think about very small delay actually. So we have this this link. How do you think how it can change the equilibrium? So we have like some road system. We have cars who optimize their delay in this road system. And then we add one super fast line to this road system. Can we make situation worse? It sounds like paradox, but usually it's the case. So when we have this situation, I think I will not right now prove that this is an equilibrium. I just give you like schedule or draft of how you can prove it. So you can start from the situation where 50 cars go here and 50 cars go here. Now imagine that one car is switching to this line. So this car have delay 30 minutes during this line, 0 minutes during this line, and slightly more than 30 minutes in this line. So it's 30, and well, it's almost 30 minutes. So it's almost 30 minutes. So the delay of this car would be 1 hour, and the delay of all other cars, remember, it's 1.5 hours. So this delay is obviously better. So if you have previous equilibrium and one car switching to this new road, then this car increasing its payoff, decreasing delay. So now imagine situation where every car using this new line. So 100 go here, 100 go here, 100 go here. Is it possible for anyone to deviate and get better result? Well, they spend 1 hour here, they spend 1 hour here. If one card deviates here, he will get also 2 hours. So it's 2 hours along this line and 2 hours along this line. It's the same. So this is the definition of equilibrium. If you can't increase your payoff, this is an equilibrium. If it's the same, it's okay. So we can't increase our payoff. We can so decrease our delay. So this is an equilibrium. So every 100 of cars go here, here, here. They spend 2 hours driving, and it is worse than original system without this super fast line. And this is actually a case from reality. It's possible to observe these events. I read about the case in New York, I think. Yeah, in New York, where some of the avenue, one of the avenue which always had traffic jams, was closed and for cars, and this gives everyone a better time of going. So average time decrease in driving decrease if you drive from one point to the other. And this is actually amazing. What is the source of this inefficiency? Well, source of this inefficiency is that this is multi-agent, many players system, and each player try to optimize its own payoff. And when rules change, everyone tries to achieve new better payoff. And here we have a situation where new equilibrium is inefficient. It's worse than the previous one. So if you destroy this road, everyone would be grateful. Okay. So this is how Nash equilibrium can be in very different system, can arise in very different systems. So this is a problem that I propose you to think at evening, maybe if you want, or maybe later. It's also a game that is solved by dominance, but it's a little bit more complicated than cards. So we have two players, and they simultaneously choose some amount, 1, 2, 3, 100. And if numbers are equal, they both got it. But if not equal, then they got minimum from two. Both get minimum, but player who named bigger number pays $2 to other guy. So if, for example, one of them named $1 and second named $2, then second one pays $2 to first player, and first player gets 3 and second gets 0. So this is the game. And the question is, what is an equilibrium, and how do you think is it realistic equilibrium? Well, how will you play in this game? Okay. So now I have two games to consider, and these games actually illustrates another important concept of game theory. So let's play game 2, and I will give you link in a second. Okay. So the rules are like this. As before, you choose number from 1 to 100. Please choose integer numbers. It's not. It's just my time to round them up. So then we calculate average without any multiplication, just average, and the winner is the player with the most distant number from S. So in previous problem it was closest, but now it's the most distant number from S. So please think and make your choice. Mhm. Remember, the most distant from the average. Okay, so we can test how many people survive after lunch. Right now it's 34. Yeah, that's true, but I mean, if I create some service, so with authentication and checking what device you use and how, it's a very long story. So it's better to rely on your fairness. And I suppose if someone will cheat it will not change the result too much. I hope, for example. And if many, I mean, if it's 100 or something answers are about, and someone will cheat, that it will not be noticeable. But and also I think I will see if you will cheat, I can say that this result is unnatural, because I know how people usually play in this game. I actually made a paper about these games in some in educational school and some special events and universities, and it will be published, I think, at October or something. It's about how people play this game and how to use it for better understanding learning process. Okay, so we have almost 40, almost 5,050. But yeah, it's a little bit strange. A little bit strange results. Hmm. Okay, so it's 55. Maybe we should. Maybe we should stop. Yeah. Oh no. Someone is sending losing answers. Yeah. Okay, I think 6 minutes was enough for play. If you really want to answer, please indicate in Slack that you need more time, because right now I will stop this game. Okay, I stopped the game. Okay, now we will. So, I mean, is it needed to explain why choosing 50 is the most losing choice you can make? Sorry, give me a minute. Oh. Okay, so when you find average, this average would be somewhere inside the line. Yes? So, if you want the most distant number from the average, you can choose 1 or 100. So if you believe that the average will be less than 50, you should choose 100. If you believe that the average will be more than 50, you should choose 1. It's dominant choice, I mean, for either belief. If you believe that this is 50, then you can choose 1 or 100, and it's the distance, it's two choices are the same. But if you choose 50 and the average is 50, then the distance is actually 0. So it's not the most distant number, okay? So we have, usually people make mixing very good. And this is summarizing before I share the result. If you believe that average will be less than 50, you should choose 100. If you believe that average is more than 50, you should choose 1. And if you don't know anything about this, you can suppose that they're equal probability or almost equal probability. So the best way of your strategy is to drop a coin, see result, and choose 1 or 100, depending of the side of the coin. And actually, the result is that you see 25 persons choose 1, and they actually lose, because the winners is the persons who named 100, because average here is 37. So average is 37, and the interesting part is that most people actually understood that they need to choose between 1 and 100. So if you already choose 99, then it's better to switch to 100 because it gives better match. If you believe that 99 is the most distant from the average, then 100 is more distant. Yeah. So instead of 99, it's better to switch to 100. So here, many persons choose 1, and this drags the average closer to 1. So persons who choose 100 actually wins. So this is the result. And this is what is called mixed strategy. So mixed strategy is then, so my prediction is not actually very good because it should be almost equal, but here we have 10% choosing 100 and 25% choosing 1. So it's like you love number 1 because of whatever reason. Okay, so to finish with the games, and I will tell about mixed strategies and some stuff about this. I want to play the game number 3 shortly after this game. So I will send you some. So here we have a slightly different condition. Wait a minute, I will see, is it open for sending 4, 3. Yeah, it's open. So you choose integer from 1 to 100. The number that is choice of maximum amount of players wins. If two numbers has the same amount of choices, the smaller number wins. So that's the rules. Please make your choice, and I will try to explain why not all numbers are the same. Are you tired? Only 10 answers. Okay, it's almost 50. But yeah, 5 minutes, it's 2 minutes to go. Okay, so we have 56 answers, and I think it's more or less active people who wants to participate here. So I will close the game, or maybe I will not. It doesn't matter actually, not now. So, as usual, winner is one. It's interesting that, well, to begin with, this is a coordination game, and here every number can be in equilibrium. So this is a game where you have very big, 100 can be in equilibrium, 93 can be in equilibrium, 56 may be in equilibrium. If everyone choose one number, or more than half choose one number, then this would be in equilibrium, and someone who deviate, he will lose. So it's actually every possible number in this game is Nash equilibrium. But not every equilibrium are the same. And this type of games are called coordinating games. To win in this game, you need to coordinate without other people, but without words, without coordination. So you need to understand how they will behave in situation where they think how you will behave. And I can show you the distribution here. So 68% are choosing one. So one is a big winner with a big margin. And you see here also 2, 7, 11, 17, 33. So it's like, well, in coordination game, it's important to take into account some cultural differences, and the point is that people are usually very good in understanding without words what other people expect. So, for example, 7 is very good number for coordinating, and 11 is a prime number, and 17 is a prime number. So you want to choose it. So 100 is also 50 is like something standing. This number standing out. So you want to coordinate around it. I'm strange that nobody named 42, which is an answer to all questions. The idea is that there is a slight, very slight hint that gives you, I presume, gives you an idea of coordination. Well, of course, we have previous game where everyone chooses one, so you can use this experience for this game, but there's also conditions that if two numbers has the same amount of choices, the smaller wins. So you start to think that I can choose any number, but since I don't know anything about this, probably if some numbers have the same numbers of choices, then smaller number wins. So I should, if I have 2 ideas or 3 about numbers that I can choose smaller of them, because it gives like plus one to the chances of winning, maybe very small one. But thinking this way, you start to think that, what is the smallest possible number that is safe to name without to be afraid that someone will beat me. So, and you understand that this is the 1, is the smallest possible number, and you understand that other probably will think this way. So you name 1, and so is almost 70% of other players without any cooperation or coordination. It's under indirect coordination in this game. And Thomas Schelling, that I already mentioned, and he was very prominent scientist, and he shared a Nobel Prize with Robert Aumann in 2005 year. And his idea was, he proposed the term focal points. Focal points is the special profiles in coordination games that stands out. So people naturally coordinate around them. For example, he proposed a game that later became a show. It was actually a real show when a group of players, they were separately put in New York in some places on I don't know, in some sites without any communications, and they should to win. The winning condition is to gather in one place in one time without any previous arrangements. So it's also a coordination game, but instead of naming numbers, they just go to the street and the cameras behind them, so they like put it in television and so on. So they go, and the surprising thing is that they actually met, and not only one group, but it was not rare thing that groups met under these conditions, because New York has a focal points, sharing focal points. And as I remember, two places where groups are met was the Central Railway Station at 12 or something, and the second was a top of Empire State Building. So it's and then later some scientists tried to make experiments on this game, and they found that some cities have these focal points and some do not. For example, in Washington, there are no focal points, no obvious place where everyone can go. And in Paris, for example, there is. I mean, everyone know where to go in Paris, I think. We can try in Slack, but yeah. So the idea of sharing is this. So simplest coordination game is you have one player, and this player can choose up and down, and we have other player, and this player can choose left and right. And if they choose up left, they get 1, and if they choose down right, they get 1. And if they choose like this, so this is the coordination profiles, and this is not coordination profile. So they get here 0. So they must understand. Actually, there are 3 Nash equilibria here. Well, 2 of them are quite obvious. First one is if my partner plays left, I need to play up. If my partner plays right, I need to play down. And the same is opposite. Okay. So there's a two pure Nash equilibrium. Okay. And there is also one equilibrium in mixed strategies. What is mixed strategy? Mixed strategy is a probability distribution over pure strategies. And this is what Nash applied to the not zero sum, but general sum game. So what is Nash equilibrium? What is mixed strategy here? Suppose my partner, which takes rows, play P1 minus P, where P is the probability to play L and 1 minus P is the probability to play R. What is my choices? If I play U up, then I get what I get. With probability P, I will get 1, and with probability 1 minus P, I will get 0. So my expected payoff would be P. If I play down, my expected payoff would be 1 minus P. I will not, right now I will not explain, but to have an equilibrium, we must have equality of these 2 expected payoffs. So equalizing, we have that P is equal to 1/2. So playing with equal probability up and down and playing with equal probability left and right is the third Nash equilibrium in this game. Nash equilibrium mixed strategy. Actually, we already play mixed strategies in some way, because when you choose between 1 and 100, the best way for you is to choose it with equal probabilities. But yeah, you didn't, but many other groups actually did this almost perfect separation. Half of them choose 1 and half of them choose 100. So it's like group of people playing strategy with their choices. Okay, so now I want to add some Python, but I think it's not time right now, but maybe we can do it tomorrow. I just give you some hint how to solve games with NashPy. So NashPy is a package which is developed by Vincent Knight, very also good scientist. He has a YouTube channel if you want to listen more about game theory, algorithmic game theory, and the calculation of different strategies and the equilibrium. I surely recommend it. But maybe you can prepare for this. So if we install NashPy and we, for example, put our coordination game inside, then we can use, there are right now implemented 3 different algorithms to calculate Nash equilibrium. It's support enumeration, vertex enumeration, and Lemke-Hausen algorithm. And I will, I'm planning, if I have time, I will plan, I'm planning to tell you about support enumeration algorithm, how it works. So if we launch this algorithm for our coordination game, we have three profiles. It's a strategy profile for each player. So we have like 1 as a mixed strategy. It's a probability distribution. But if you have probability distribution where you have where you play one strategy with probability 1 and other with probability 0, this is actually pure strategy. So mixed strategy is a generalization of pure strategies, and mixed Nash equilibrium is a generalization of pure Nash equilibrium. So we have 1, 1, yeah, 1, 0, 1, 0, 0, 1, 0, 1. It's two pure Nash equilibria, and 1 is 0.5, 0.5, 0.5, 0.5, and this is a mixed strategy equilibrium. So summarizing, what is best about Nash equilibrium? Well, it always exists under mild conditions. Well, actually, Nash showed it for every finite game, and later it was generalized for infinite game of some sort. So, put in simple, almost every game has Nash equilibrium. Not every, but almost every. But in mixed strategies. So it's always exists here. I didn't put it in mixed strategies. So sometimes it is in pure, but sometimes it's only in mixed. And it's very natural concept that arises in many applications in every field where you have strategic decision making. So what is the bad about Nash equilibrium? Well, we already see that it can be inefficient, like in prisoner dilemma or in Bayes paradox. It's hard to compute usually. If you have big matrix, first, it's not easy to calculate at all, especially if it's not pure, some of those pure equilibrium. And second, if you have like matrix with 5, 6, 7 strategies, the number of possible Nash equilibria rises. So many different Nash equilibria can be. And yeah, it's multiple equilibrium is like common situation. So if you have class of games where you have the only Nash equilibrium, it's like birthday present. So okay, I think we can go to the questions right in a few minutes, but I give you some remarks. And so we have this matrix, and my question is, how many Nash equilibria, how do you think, are in this matrix? You can use NashPy for answering, but try to say, give some intuitive, how do you think? But you have this matrix. You are playing for the both sides, but separately. And how do you think? What is the obvious Nash equilibrium, and how many are this? So to finish, I recommend you to see a scene from the movie Beautiful Mind about John Nash, and you can just, I will not provide you direct link because I need to put it in iPad or something, but you can just search in YouTube by this title, and this is a bar scene, John Nash equilibrium game theory, Beautiful Mind. So this is an example of how Hollywood misunderstands concept of Nash equilibrium, and when you do this, you will understand better this beautiful viscosity comics, because it's actually a difficult joke if you're not in this. So now I'm ready for questions, and yeah, thank you for your patience, and we will continue tomorrow. I plan for tomorrow some some applications which are not obvious, like bargaining, negotiations, strategic moves, repeated games, probably coalitional and cooperative games, and matchings. So I want to give you some taste of every major part of game theory, so you will have at least ideas of what is going on. Okay, so now you have, I have questions. Okay, yeah. So yeah, if we kill A, then it would be for persons. Yes, so it's not working. So we should steal his cards. It's enough. Yeah. Could you suggest any readings for comparison of game outcomes across culture? Yeah, it's I know such papers. I think it's the best way to begin with is Colin Kammerer experimental behavioral game theory. Colin Kammerer. It's actually I will tell you about this tomorrow in behavioral game theory part. It's about ultimatum game and how different culture plays it. It's actually different, but you can also Google trust games. I think there is a paper from Technion, Israeli, about cross-cultural analysis of trust game, how different groups trust each other under special setup. Yeah. But in Kammerer, there is a cultural differences also highlighted. Any other questions? Is the existence of focal points? Well, it's I think. Yeah, I think it's connected with cognitive processes because as in thinking fast and slow, you try to find some idea to simplify your thinking process, and if you have very close outcomes in a coordination game, then you need to think hard how to choose one. And then you understand that one is a little bit different of other. So, and this is I idea that helps you to solve the problem. So it's not this equation actually. I'm not a specialist in cultural like game theory or something, but I just know that usually people very good in finding these focal points. Okay. Interesting question could be, is it possible to learn some algorithm to look for these focal points? But yeah, I didn't saw any, I didn't see any research about this, I believe. So if table with the last task, you mean to the table? Yeah, you mean this? Okay. And just make screenshot. I think it will be fine. Also remember about the game with coins. You can also try to solve it. It's rather, I think it's interesting. And you can, I think you have this YouTube recording for the end of the school, so you can always find this moment and see. Mm. Mm-hmm. Okay, actually, I have one last game. Maybe we can finish with this if you still, but or maybe we can do it tomorrow. It's actually quite interesting because it's like open question. What is timeline? I think it's already, yeah, we started. Yeah, it's 1 hour and a half. Okay, if no questions, then have a nice day.